fire tornadoes cannot be ignored.
Hot, vibrant, loud. This is our very own fire tornado. For our ME Fluids project, we wanted to do more than just make cool fire. Our burning question was, how does the gap space in the column control the height of the flame? In other words, is there a mathematically optimal way to build a fire tornado?
Boom, here's the math. So first we have the gap ratio and the vane angle, which you learned about 5 seconds ago, so you never remembered it.
Oops. Well, here's an explanation of the vane angle and gap ratio. We surround a small alcohol flame with a cylinder that's split into 2 halves. By sliding the halves, we create adjustable openings on the sides. We define a gap ratio, phi, as the total gap area divided by the column's cross-sectional area. Back to the math.
This is the equation for the swirl number, for an asymmetrical swirl, which is what we have right now with phi. We simplified this down to this ugly equation, so we said, you know what, we need to simplify it some more. And we simplified it to this equation here, where K is the column geometry and the vane design. It kind of is a constant that holds both of them together. But then you might be wondering, how do we get the flame height? How do we know how tall the flame is? And we get that from using a Navier-Stokes with a Boussinesq approximation. And we have 3 assumptions that we make. Axial gradients dominate the radial, viscous terms are small compared to buoyancy and inertia, and pressure is nearly hydrostatic. Plugging these assumptions back into this equation, we're able to find the baseline height for no swirl. And then using that, we're able to figure out an equation using a quadratic fit model to find the height as a function of phi, as a function of the gap ratio, which is shown here. And then to find the optimum gap ratio, we set the derivative of the height with respect to phi equal to 0, and we end up getting this equation here. And if you ever thought about switching out of ME, the answer is never.
Air rushes in through those gaps, gets turned by the walls, and starts to swirl. The swirl stretches the flame into a tall, narrow column. The stronger the swirl, the taller we expect the flame to be, up to a point. We then use Tracker to measure the average flame height for each gap ratio, then normalize by our baseline height h0 from the almost no gap case. Here are the results. As the gap ratio increases from 0, flame height rises, reaches a peak, and then decreases again as we overvent the column. Had our column been taller, our data would have been more easily measured. The data shows at small gaps the swirl is weak and the flame is short and puffy. At an intermediate gap near phi star, swirl is strong, the hot core is compressed, and the flame shoots up into a tall, tight column. At very large gaps, we lose confinement, the vortex breaks down, and the flame height drops again. So by combining Navier-Stokes, a swirl number scaling, and a simple quadratic model, we show that there really is an optimal gap ratio that maximizes fire tornado height, which also tells you the most efficient setting for marshmallows roasted per unit gap. But please don't try this at home, unless you also bring safety goggles and a fire extinguisher.